So we're waiting for Matt, right?
Yeah. Jean-Jacques already here.
Hi, Jean-Jacques, how are you?
Hi, how are you?
We're going to start very soon. He did better than me. Just to make sure.
This is just setting our expectations.
Setting expectations.
Yeah.
Yeah.
There was a weird offset issue there.
His PhD was expensive. I had to spend a lot of money in buying new hardware.
Sumeet, did you keep all the broken parts, all the broken propellers?
Surprisingly, that quad rotor is still going, and we got experiments from it last week.
Awesome.
So it's still good.
All right, I think we can get started.
Yeah.
So it's my pleasure to introduce Sumeet. Sumeet has been one of the very first students joining my lab, and in about 4 or 5 years, I don't forget how many years I've been here, he's been working on a very broad range of problems, from trajectory optimization to decision making, applied to autonomous cars, satellites, airplanes, aircraft, UAVs. And I like to say that I told him many times that a third of his PhD was very qualified as a PhD in an effort to make him graduate. But he kept doing stuff, and I was very happy about it. We had a lot of memorable interactions. First of all, he has superhuman capabilities. He's the only person I know that he can work on paper for 3 days straight without sleeping. I don't know how he does it. So, new students, when they see him working toward the paper, get scared, saying, I don't want to join the class, because if this is the expectation that I can't sleep for 3 days, that's no way I can do it. Just mentioning one of the interactions, one of my favorite stories, as someone knows. When he joined, we wrote the first paper, and we had a lot of iterations, and I was very picky about his technical writing and so on. And then after the paper was submitted, I approached him saying, look, it's hard to be a non-native speaker in the United States, because of course you have to write in a language that is not your native language. So there are a lot of programs if you're at Stanford to help you with English as a second language, encourage you. And he said, Professor, I'm Australian. At the time, I realized that there are a lot of different accents. So after 4 years, first of all, that allowed me to better understand Karen, who is also Australian. And after 4 years, at least, I think I can understand well the Australian accent, and he can understand well the Italian accent. And then for the more technical stuff, I leave the stage to Sumeet.
Cool.
The stage is yours.
Thanks, Marco. All right, everyone, thanks so much for being here. Today I'd like to talk a little bit about the work that I've done in control and decision-making for robots in uncertain environments. So formally, my research goal has been to try and create analysis and synthesis tools for planning and decision-making for robots that are operating in uncertain environments. And so algorithms that can actually formally understand uncertainty and deal with robustness at all levels of model-based autonomy stack. So when I talk about a model-based autonomy stack, specifically what I refer to is a traditional view of a robotic autonomy stack, which at the top level starts from a perception loop, where in this case you have an array of sensors that are accumulating information from the world and creating some sort of a world representation. This then feeds into the dynamics engine of your robot, where the robot tries to reason about its own dynamics, as well as the dynamics of any other agents in its environment, for instance, any humans. This then feeds into the planning module, where the robot tries to create plans for the robot at both at the task level and also at the continuous trajectory level. And then this finally rolls into the controller, which tries to execute the plan generated by the robot, ideally with some sort of a feedback tracking controller to give you some sort of a robustness guarantee. So most of my work in my PhD has focused on the dynamics, planning, and control aspects of the autonomy stack, and to formally motivate why you need to really think about robustness when you're trying to deploy these robots in real life. There's a video of the first project I did at Stanford on decentralized formation control. In this case, the robots are trying to achieve a tetrahedron formation without communicating with each other. And you can see that the top quad rotor nearly pushes the one into the ground due to the one at the bottom into the ground, simply due to a downwash effect. In this case, there were no collisions, and the thing didn't collide with the ground, and everything was stable. But this is what happens when you get that reactive control policy wrong. And it was just a very simplistic collision avoidance control policy. It's not just my drones that seem to suffer from these sort of issues. This is a news report at the end of 2016 on Facebook's Aquila drone. As it was coming into land, it experienced some unexpected strong winds on its wings due to a wind gust. The autopilot basically went into an emergency mode, and it was unable to cope with those strong winds, eventually causing it to crash. And so what this basically tells us that this core task of being able to compute and follow dynamic collision-free trajectories for a robot in real time is actually still a really challenging problem, especially for agile robotics. And if we try and break this down into what the key challenges here are, the first one is that you need to be able to generate dynamic collision-free trajectories for highly nonlinear systems in real time. This means solving a constrained trajectory optimization on the fly, which is a really difficult thing to do. The second thing is what happens, of course, when there are wind gusts or other external disturbances that act on your system that try and basically deviate your robot from its intended path. The third one is what happens when the basic physics-based models that you'd use to derive the trajectories and you use to derive the controllers, what happens when these models are actually inaccurate and you actually don't have a good model simply because you neglected a lot of effects in your modeling procedure. So here potentially we might need to use some sort of a learning-based technique to try and augment our dynamics model. So my contributions within these three areas span essentially starting from planning with model mismatch, where essentially you plan using a much simpler kinematic model that you can do actually in real time, but you still somehow are able to give guarantees on the full complex nonlinear dynamics of the robot. And the idea behind doing this is to try and compute essentially a bound between two dynamical systems, and you use that bound to generate trajectories on the fly. The second step is once you have these dynamically feasible trajectories for your nonlinear system, how do you guard against external disturbances? And so here the contribution is to be developed, the contribution here was to develop a generalized scheme for designing nonlinear feedback controllers that give you a bounded input, bounded output property with respect to disturbances. This property basically takes the form of this tube-like shape, where this tube is the set of all states that the robot might occupy as it's rejecting disturbances following a trajectory. So you can use that tube now as a collision margin when you're generating trajectories. And then the third contribution is in the frame of learning dynamics, where essentially we accept the fact that we've made some simplistic modeling assumptions, and therefore we try and augment our dynamics model using actual data generated on the robot and see what actually happens when we try and use a learned model for doing trajectory generation and feedback control. So these last two topics really will be the focus for today's talk, but I'd just like to give a quick overview of some of the other work that I've done to complete the sort of model-based autonomy stack formulation. So the next sort of problem that I ignored in this list so far has been how to deal with other intelligent agents. And intelligent, in this case, is a loose word because it does include humans as well, who are not always rational drivers. For instance, if you consider a situation like this, imagine your autonomous car is coming in onto the freeway and trying to merge, and there's another car that wants to exit at the same time. Now, this is a fairly complex interaction, and there are various videos online of self-driving cars that have struggled to do this, which I'm not going to show for copyright purposes. But at least Google has admitted that this is really a challenging problem. It really is an exercise in negotiating where you're trying to figure out who's going to be the person who gives way and who's going to be the person who actually accelerates through this maneuver. Implicitly, what your autonomous car needs to be able to do is to reason about the range of possible actions that the human driver might take and to use this prediction model within the planning architecture for the robot itself. One potential way on how you can build prediction models for how humans behave is to take the inverse reinforcement learning paradigm, where essentially we assume that humans make decisions by trying to minimize some cost formulation forward in time. But what a lot of research has actually shown is that this is actually a poor model for how humans make decisions, especially when it comes to risky situations. So the idea that we developed is to replace this expectation operator, which is just a linear operator on the space of random variables, and replace this with some random operator rho, where this rho operator is now nonlinear on the space of random variables. Specifically, what this rho allows us to do is to capture the fact that people not only might care about the cost of a collision, but really what matters in the end is the probabilities. Essentially, how do different people view probabilities in the event? And this is simply can change from one person to another person. And therefore, we developed a paradigm where essentially we not only try and back out from demonstrations from a human what the internal cost function might be, but as well as what the internal risk preferences as captured by this rho metric might be. We asked participants to behave in a driving simulator and essentially put them into a risky situation. And what we actually found is that you do, in fact, need both the cost function formulation as well as the risk preference model to try and accurately predict different driving styles. So on the left here, you have the optimistic driving style where participants were trying to tailgate the front robot car. And on the right-hand side, you had risk-averse drivers who tried to always maintain a safe distance away from the robot car. And then finally, I'll talk a little bit just to mention some of the more recent work we've been doing on, again, completing the entire autonomy stack by looking at the notion of uncertainty and robustness with respect to perception. Specifically, we've been trying to analyze this sort of recent state-of-the-art results that have come out that have shown that state-of-the-art deep neural networks are surprisingly brittle when it comes to image classification. And so even with just imperceptible noise added to a picture of a panda, this picture is still clearly a panda, but state-of-the-art classification networks can easily make this mistake. This might seem sort of an inconsequential mistake, but you can imagine an autonomous car that misclassifies a stop sign as a give way sign simply due to a small set of black and white stickers can be much more disastrous. So some of the work that we've been doing here with collaboration with DeepMind Research is to try and formulate what is the minimum distance in pixel space that you need to apply to distort your image before your deep neural network makes an incorrect classification, and therefore use this distance within the overall training procedure as well. So overall, my entire approach towards developing robustness within model-based autonomy is to take a holistic approach where we focus on problems all the way down to trajectory optimization and control, to the mid-level stack where we're trying to make decisions not in terms of trajectories, but more in terms of higher-level decision modes, and then finally addressing robustness at the perception stack as well. So again, the focus for today's talk will be on robust motion planning and learning dynamics. And before I get into that, I also just want to mention some of the other work that I've done in various application regimes, including drag-free control for microsatellites, formation control for drones, which I showed earlier on in the video. Some of the recent work that we've done with MaxLab on cooperative transport for heavy objects using multiple drones without any communication, as well as some recent work with Joe Lorenzetti, also in ASL, on reduced auto model predictive control, where we essentially have a much higher dimensional system that we want to control, and how we can generate lower dimensional approximations that can still give you sound guarantees when you're trying to use it to control the full auto system. All right, so we'll get into the first part of the talk today, which is on robust motion planning. So the robust motion planning basically entails solving the following problem. You want to take your robot to go from some arbitrary initial location to a desired goal location while minimizing some cost function. This cost function basically takes the form that, for instance, you want to minimize the time taken to get to the goal and maybe some formulation of how much control effort it takes for you to get there. You're subject to the nonlinear dynamics of your robot. You have some state space constraints, for instance, obstacles. You have limits on your control authority. You have obviously the endpoint constraint that you need to end up at your goal location. And now what we're additionally adding in is this W of t term, which is a disturbance that's acting on the system. In this case, the only assumption we're going to make on the system is that this disturbance is completely bounded, rather than taking any stochastic assumptions here. So the challenging part of this problem is to be able to solve this constrained trajectory optimization problem in real time in a dynamic fashion, for instance, using receding horizon control. And the key insight of all my work is the fact that robustness has to be factored in to the planning stage, and it can't be simply done as a reactive control policy. Clearly that failed when I tried to do that with my formation flying robots. So the key idea of how to actually solve this problem in a tractable way is to break up the planning problem into a nominal component and some feedback controller. So the idea is that you generate a nominal trajectory which corresponds to this nominal control signal, U star of t, and then you try and stabilize your system along this trajectory using some sort of a feedback controller. And so the idea is that this feedback controller gives you a sort of an invariant tube-like region around any trajectory that you might generate, so that when you use this feedback controller to track the trajectory, you're guaranteed to stay inside the tube. This means that when you generate the original motion plan, you can now use this tube as a collision margin as a way to guarantee safety with respect to disturbances. This is not a new idea. The whole concept of planning with tubes and sort of sequentially composing these tubes to construct a global plan, this is definitely not a new idea. But what's really the challenging part of this problem is that how can we actually construct this feedback controller? We want some sort of an automated way for an arbitrary nonlinear system to be able to optimize this feedback controller that gives us this sort of tightest possible tube so that we're putting the least amount of restriction on this plan as possible. If we look within the literature, and primarily I'm going to focus here on the robust planning literature rather than the stochastic planning work as well, the spectrum really goes from the end of conservative solutions all the way to exact formulations. On the conservative end of the spectrum, the typical approach is to try and linearize your dynamics around a trajectory and then use some sort of a continuity argument to try and give some sort of a guarantee with respect to uncertainties that you've ignored in your dynamics from linearization and also with respect to disturbances. Naturally, this is going to be extremely conservative because you're now lumping in all the nonlinearities that you're ignoring in addition to all the disturbances that the system's actually experiencing. On the middle end of the spectrum, you have the formulations such as LQR trees, where essentially builds a tree of pre-computed trajectories and LQR controllers around them, and then basically does a certifying stage offline where it tries to give you a guarantee on what is the safe region of the LQR controller for each trajectory. And while this is actually quite a cool approach, the main limitation here is that you need to know your environment a priori, in the sense that all these trajectories need to be pre-computed for a given obstacle environment. And so this is not really a suitable technique for real-time planning. On the exact end of the spectrum, you have the differential gain formulation, which essentially poses the problem as control as the agent that you control and disturbances as a disturbing agent that you're unable to control that acts adversarially on your system. And so you end up with this game formulation, which in the end, to compute the solution of the game, you have to solve a fairly complex Hamilton-Jacobi partial differential equation. And the main limitation here is that while this gives you the exact solution and it gives you the exact controller and tells you exactly what to do at any given state and time, this is really difficult PDE to solve simply due to scalability issues with dimension of the state space. There's been some recent work by Sylvia, for instance, in Claire Tomlin's lab, who's tried to alleviate some of these issues by formulating the differential game in relative dynamic space. But unfortunately, this is still not a fully scalable approach to handle higher dimensional systems. Again, on the middle end of the spectrum, we have techniques such as sliding mode control developed at MIT, where essentially the idea is to use the fact that your system might be fully invertible to essentially cancel out the nonlinearities and therefore impose on top of that some sort of a stable closed loop dynamics behavior that rejects disturbances. But again, the limitation here is that the system has to be fully invertible for you to achieve those sort of guarantees. And again, the idea of barrier certificates is basically to build an artificial repulsive potential field around any obstacles. And therefore, it suffers from a similar issue as LQR trees in the sense that you need to a priori know your environment. So as I mentioned, the key sort of idea for all of our work is to take these notions of funnels and tubes to sort of sequentially compose them to construct a global plan. But the key sort of distinction with respect to the state-of-the-art that's also taken this approach in terms of funnel planning is that the state-of-the-art essentially pre-computes a set of stabilized trajectories as well as a set of stabilized funnels. And then basically at runtime basically sequentially composes these fixed set of funnels. What we would like to do, however, is to be able to give this sort of an invariance or this funnel guarantee for any trajectory that we might generate online. So in the sense, our focus really is on the control system feedback design that gives you invariance guarantees for any trajectory. So introduce how we're actually going to be able to do this using the framework of contraction analysis. And I'll show how this can be used as a form of control-based synthesis, contraction-based synthesis. And then finally, how it can easily be integrated into existing motion planners. Right, so the basic idea of contraction theory is to analyze stability on an infinitesimal scale. So the idea is that if you can look at two trajectories that are infinitesimally close, you can use the stability of these two trajectories to try and infer some global properties in terms of the stability between any pair of finitely apart pair of trajectories. And I'll show how this procedure essentially goes. But contraction theory has one of the big advantages in that it drastically simplifies the closed loop stability analysis for a lot of complicated nonlinear systems, and accordingly has been adopted in a lot of applications, ranging from process control to SLAM as well as recently stochastic control policies as well. The focus, however, in terms of contraction theory for today is to see how we can use this tool as a means to construct stabilizing feedback controllers. All right, so the next 3 to 4 slides will get a little bit math intensive as I describe the details of contraction theory, but I'll try and go through it slowly. So the idea is, let's start with a dynamical system, a control system, which is given in control affine form by this differential equation. And let's say I give you some fixed state and control trajectory. About this state control trajectory, I can define delta x and delta u as an infinitesimal displacement about this trajectory. The key point to remember is that this displacement is not a physical displacement in the state space. It's a vector in your tangent space. It represents a differential length element. We can actually write down the dynamics for this displacement as simply the Jacobian linearization of your dynamics about any given trajectory. And now the idea of contraction is to say is that if I can find some positive definite function where this quadratic form is quadratic in these differential displacements in the variations, and the matrix part can be state varying, and as long as it's positive definite, if I can find some positive quadratic function such that for any given trajectory, there exists a differential controller, so a mapping from state control and variation to differential control variation that makes sure that the time derivative of this v function is always negative definite. If I can find such a function, then we call, and basically the image that goes along with this is that if you remember the traditional Lyapunov style images of stabilization, what essentially we're saying is that this differential controller is making sure that this continuous spread of Lyapunov functions around along any given trajectory is decreasing in time. And the spread essentially is being measured by the strength of this function v. If we can find such a matrix M that comes with this guarantee that there exists this differential control delta u, then we call the matrix M a control contraction metric, and the function v a differential control Lyapunov function. So there's a very important reason why we actually call it a differential control Lyapunov function. If you recall some of the basic theory on CLFs for just stabilizing to an equilibrium point, a CLF basically says that it is some non-negative function such that when control can do nothing to affect the derivative, the time derivative of this function, the system has to be naturally stable. And this is necessary and sufficient to guarantee that there exists some sort of a feedback controller that gives you a stability guarantee with respect to an equilibrium point. And the standard image that goes with this sort of analysis is, you can imagine a bowl-like function that represents the energy of your system. And basically, as you're going along, the control is making sure that you're going to lower and lower level sets of this function. The difference now is that in the differential CLF case, we're still writing down the time derivative of a v-like function, but now this time derivative is in terms of the variations. So we get an exact analogous condition where basically we say that if the term multiplying the differential control is 0, then the system has to be naturally stable along those differential displacements. And therefore, the standard image that goes with this is this continuous spread of a Lyapunov function that goes along, that's swept along a trajectory, that's decreasing along your trajectory. So at this point, all I've really mentioned is how you can guarantee stability of infinitesimal or differential displacements. So how do we actually go from that to actually stabilizing a pair of finitely apart pair of trajectories? So let's say that the trajectory that we want to follow is given by the red curve, x star of t, and the trajectory that we're actually following is x of t. So what we're going to do is at each point in time, we'll think about all the family of curves that connect x star of t and x of t. So in this case, C of s is simply outlining this curve that connects those 2 points. S is just an arc length parameter, and delta c is essentially just the tangent vector along that curve. We can assign a length to this curve by simply taking the line integral of this positive definite function v. So if you imagine if the matrix M of x was just constant, then the shortest curve that connects x star of t and x of t is just a straight line. But if this function matrix M of x is state varying, you can imagine me trying to minimize this integral quantity to find the shortest length between these 2 points. This can take an arbitrary shape. So at each point in time, we'll find this arbitrary shape, this curve gamma that connects x star of t and x of t, as a curve that minimizes this length quantity. And with a slight abuse of notation, I'll call this E basically the Riemannian energy, or energy for short from now on. Then at each point in time, you can imagine that there's a spectrum of solutions that lie in between the trajectory x star of t and the actual trajectory x of t. And this spectrum of solutions is basically being defined by taking your nominal control signal that lies along the red curve and then basically integrating the differential control element along this curve gamma. So the idea here is that each, the form of this differential control element that you've taken along this curve satisfies that stability property, which basically says that for every pair of infinitesimally close trajectories along the spectrum, this differential control is making sure that those two trajectories converge to each other. And then the final part of the proof essentially shows that if you take your control to be the nominal control plus this integral of this stabilizing differential control, you can show that the global energy between those two trajectories also satisfies your exponential stability property at the same rate, lambda. So there are a couple of really important points to remember here. The first one is that to go from step 2 to 3, there's a lot of subtle details essentially on how you can show that just using differential stability pairwise everywhere is sufficient to give you global stability between two pairs of trajectories. But the other really important thing here is that none of this is approximate analysis. I haven't done any form of approximate linear analysis that's only valid in the vicinity of a given trajectory. This is a form of doing differential analysis everywhere in the state space and then using integration to then establish stability on a global scale. So there's no approximate analysis here. So there's the basic sort of overview of what we've covered in the last three slides is that we've gone from a global notion of Lyapunov functions and stability to a differential notion, which essentially we put together by analyzing differential stability everywhere in the state space and then giving you a global sort of a result. There are three key advantages of why actually we might want to do this sort of a tedious, so far at least seemingly tedious construction. The first one is that this integral method that I described of constructing the stabilizing feedback controller, this only guarantees that there exists a stabilizing feedback controller, but it may not be the unique control. So it's also a rather tedious thing to be able to do at every single point in time at runtime. So what we can show is that you can use this energy-like function exactly like a CLF. So the idea being that you can pick any control that makes sure that the time derivative of your energy is decreasing exponentially. Oh, sorry, your energy function is decreasing exponentially. And what basically contraction theory, all that preceding analysis essentially establishes that at every given point in time, there will always be some control, feedback control K, that makes sure that the set of all feedback controls that make sure this property holds is non-empty. Meaning that every point in time, I always have some feedback control guaranteeing that the overall system can be made to be stabilized exponentially. And so now the nice part about this is that the quantities A and B are just analytical in the expression of the dynamics, as well as the curve that you've computed. And therefore, you're now free to just simply pick, for instance, the smallest element of the set K. The second key advantage comes in terms of disturbance rejection, which was, if you remember, our primary goal. So normally, if there are no disturbances in the system, you have a nice exponential stability property. If you have disturbances acting on the system, you get essentially an upper bound on the time derivative, where essentially you have the nominal part, which is just the exponentially stable part. And then you have two additional components, which essentially come from bounding the singular values of that M matrix and the bound of your disturbance. Essentially, the result of all of this analysis is that you can show that the energy will always be upper bounded for all time by some finite amount, where this finite amount scales directly proportional to the amount of disturbance that acts on your system and inversely proportional to how aggressive your feedback control is in terms of contraction rate. So what this physically looks like is that if I give you any nominal trajectory, at every given point in time, my state will always remain inside this sort of an arbitrary shape formation, and this ball essentially can be arbitrarily shaped simply because of the fact that the way we measure distances between points is through the integral of some state-dependent line quantity. So this is a nice sort of a guarantee, but unfortunately it's not very useful to be able to do robust motion planning, because every single point in time you'd have to compute what this ball looks like and then intersect the ball with every single object that you might collide with. So we can actually do a simplification here where we just take an ellipsoidal outer approximation, and this basically now gives us a fixed sized shape that we can use to run collision checking, and this is now our collision margin that we use when we generate feedback, when we generate nominal plans online. The key part to remember here is that now we've achieved our goal. This sort of a guarantee is independent of any of the trajectory that we're trying to track, because this result comes purely as a result of the feedback controller. And more importantly, this is a result that's actually more powerful than feedback linearization. There's no need to invert your dynamics. And therefore, this form of constructing controllers is strictly a more general approach. The third key advantage is how do we actually find this matrix M of x that gives us these nice guarantees. So to sort of set the stage for computation, if you think about how we construct controllers for linear time invariant systems. So let's say I have an LTI system right here. Then the traditional Lyapunov approach of constructing controllers says that if I can find some positive definite matrix function in terms of this matrix P, then the CLF condition basically, again, says the exact same thing. If control can't do anything to affect the time derivative of the function V, then the system has to be naturally stable. If we just do a quick change of variables by taking the inverse of the matrix P, we actually get a convex condition in terms of the matrix W. And then we can put this into a standard STP solver and get our solution for W and get our solution for the feedback controller. In the exact same way, we're going to just consider the inverse of the matrix of our CCM M of x, which we'll call W. And then what sort of the nice property of this is that the CLF conditions basically come down to a set of equalities and LMIs. So in this case, we have, of course, the positive definiteness constraint. We have an equality constraint, which essentially boils down to a structural property constraint on the matrix W. And we have an LMI, which for a fixed contraction rate is essentially its affine in W. So we have a set of convex conditions, which if we were able to solve, gives us a certificate that this system can be exponentially stabilized. The problem, however, is the fact that these conditions need to be satisfied everywhere in the state space. And this is not a surprising result, because we're doing this analysis everywhere differentially on our state space. So how can you actually solve an infinite dimensionally constrained optimization problem? So this generally falls under the class of semi-infinite optimization, where typically you're trying to minimize some finite a cost function that depends on a finite number of things subject to an infinite number of constraints, or functional constraints. And there are various solution approaches, for instance, approximate solution approaches that are being proposed, for instance, based on sampling, which we've done as well. But the technique that we used in this particular work is sum of squares optimization. So basically what sum of squares says is that I'll restrict everything to polynomials, and then my CCM conditions are equivalent to just checking the non-negativity, because basically I'm checking that a certain matrix is negative definite over an entire space, so this is basically equivalent to reformulating as a non-negativity constraint. This already is NP hard, however. So what SOS basically does is that if I want to show some polynomial P of x is non-negative everywhere, if I can rewrite it as a sum of squares of other polynomials, then this is a sufficient guarantee. The nice thing is that you can encode this exactly as a semi-definite program with a whole bunch of linear equality constraints. The problem, of course, is that the size of this matrix Q that we're trying to find that gives us the certificate of sum of squares, the size of this matrix scales exponentially with the dimension, with the degree of the approximation that you're using in your polynomials. So I'll come back to some of these scalability challenges later on. But at least what we have right now is a sort of full pipeline where, given any dynamics function, we go through the offline stage of trying to find this contraction metric using sum of squares optimization. With this, we get the ellipsoidal tube bound. And then at runtime, we can use any motion planner that can generate motion plans online, as long as we use this ellipsoid as a collision margin. So I'll illustrate this on a 3D quadrotor. In this case, we take a 10-state model of position, velocity, attitude, and thrust. And our control inputs are the low-level angular rates as well as the thrust derivative. In reality, we actually just integrate the thrust derivative, and that's how and those are the commands sent to the low-level autopilot on the quad. We parameterize W just in terms of the attitude and the thrust. And the reason why we did this is because when you actually look at the CCM conditions, it naturally captures the invariances of your dynamics. So in this case, the quadrotor dynamics don't depend on position. They don't depend on yaw. And so that same sort of invariance gets captured within the stability property as well. We impose some limits on the attitude. So in this case, negative 60 to 60 degrees is a fairly aggressive range for bank angles. We put some limits on our control. And then just to give an order of magnitude of what this actually gives you is that if you imagine there are about up to 0.1 Gs of wind gusts, which is not a small amount, acting on this quadrotor, you get a tube bound that's approximately 1 meter when you project it into your translational space. And I'll show experiments in a second, but the nice thing to remember here is that a feedback linearizable controller, so a fairly standard approach for quadcopter control by inverting your dynamics, actually turns out to be unstable when it was subject to noise in measurements. And before I show the video, the way we actually ran our experiments was to compute this disturbance bound with respect to an unmodeled drag force. So basically, we ran a whole bunch of calibration flights first, we computed a drag force model for the quad. With that drag force, we came up with an upper bound on how much disturbance might act on the quad, and that disturbance bound is what's actually used to plan trajectories. So on the top left, I'm basically just showing an animation of what the trajectory planner is thinking online as it's using this tube as a collision margin going forward. You can see some instabilities coming from ground effect. And basically, all that's happening is it's projecting that fixed size tube forward and using that for runtime collision checking. In this case, all error bounds were satisfied. And as I mentioned, the bound was computed by assuming a fixed maximum amount of drag force in the quad. So in this case, this was purely to show that the entire planning and control pipeline works. We also went ahead and pushed the quad to its absolute limits. And in this case, the actual computed bound is not theoretically sound with the obstacle environment that we've set it up at. So this was more just as a test case to see just how well it can track trajectories when subject to its absolute limits. Just to give you an order of estimate, like it gets up to about 55 to 60 degrees of bank as it's going around, the pole. So it really is at its absolute limits at this point for this particular quad anyway. When we look at the tracking bound performance over essentially the entire race course, what we can see is that the most amount of deviation basically happens exactly where we expect it to be in the places where it experiences the most amount of drag. And what an interesting effect that we actually observed here is that as we ramp up the speed of any given trajectory, what I'm plotting on the x-axis here is simply the actual energy divided by its theoretical upper bound based on the drag force. And the y-axis is simply the cumulative probability, the amount of time it spends less than or equal to that particular bound. And what we can actually see is that as the speed of the trajectory actually increases, it spends a greater proportion of its time at a lower proportion of the theoretical bound. And this simply is due to the fact that, if you remember, the feedback controller checks at each point in time whether or not it needs to do anything to maintain stability of the system. And if not, it basically switches off the feedback for that time instant. And so as the speed gets higher and higher, basically the feedback control is more and more active, maintaining tighter control of the robot. So I'll come back towards the end of the talk to talk about limitations of the approach, but I'd just like to move on to the second part of the talk, where essentially having addressed the issue of planning with wind gusts and briefly the planning of how you can even generate these plans in real time using simplified models, I'd like to talk about what happens when basic physics-based models are insufficient, and we now need to use some sort of a learning technique to try and build a model for the system that's useful for feedback control. So the problem that we want to solve here is basically to plan with unknown but deterministic dynamics. So a typical model-based reinforcement learning pipeline looks as follows. You observe some trajectories of your system, you record tuples of state, control state derivative, or the next state, and you try and build some sort of an estimate from the model, which you then use to generate new trajectories and basically repeat the loop. But what researchers have sort of universally noted is that this sort of a model-based paradigm fails to keep up with model-free methods, especially as you as you increase the amount of data available to your algorithm. And we believe that the primary issue in this entire loop actually comes from this step when you generate new trajectories, where there's absolutely no guarantee within this entire learning algorithm that when you generate these trajectories, they're actually followable for the robot, or whether they're even controllable or even at least stabilizable with some feedback controller. So if we look at how model-based RL is treated within the literature, there's sort of two primary schools of thought. In the first two approaches, you basically look at dynamics fitting purely as a machine learning task, as a statistical estimation task. So either you treat it as a pure regression problem where you're just trying to improve the one-step prediction of the model, or you try and build some sort of an uncertainty-aware model where you attach probabilistic models to capture the uncertainty in your model, for instance, using GPs or linear Bayes estimation. And then this is usually combined with some sort of a stochastic control approach, which essentially tries to give you some sort of an invariance guarantee with respect to the uncertainty that's encoded in your dynamics model. The main limitation here is that basically these two approaches don't account for the end effect. That nowhere in these two pipelines is the knowledge, the fact that I'm going to use these dynamics for feedback control and trajectory stabilization. It's viewed purely from a statistical estimation point of view. And therefore, the kind of guarantees that you get from this are usually quite loose And therefore, you typically have to resort to very conservative strategies simply due to the intractable computational issues with GPs and things like bootstrapping, for instance. The other two approaches that go with the second school of thought is to try and take some sort of a closed-loop learning approach, where the idea is to take some knowledge of the task actually at hand, so in this case, trajectory generation and feedback control, and try and incorporate that within the learning loop as well. So the idea of the hybrid model-based model-free approaches is to learn dynamics models that are basically such that the induced policy from those dynamics models gives you the best performance on a given task. The main issue with this sort of an approach is that the dynamics models that you're likely to learn are going to be distorted models of your true dynamics, simply because the system has basically exploited some sort of a weird nonlinear effect, potentially in your simulator, that allows you to get much better performance on the task, even if it means learning strange or weird dynamics. In the imitation learning approach, however, what you essentially try and do is try and just learn the closed-loop dynamics of an end effector, or the output space of your robot. And once you've learned what a nice stable motion looks like for the end effector, you use inverse dynamics to actually figure out what the internal motor torques need to be so that you can realize that desired closed-loop motion. What we, however, want to propose is that these sort of model-based RL techniques so far in the literature, they're not accounting for the closed-loop effect of the downstream application. So specifically, what we want to propose is that we want to learn a dynamics model that minimizes the regression error plus some regularization term, subject to the constraint that whatever model we actually learn is stabilizable. It can be used for feedback control. So the way this should really be viewed is that this is simply a form of hypothesis pruning that's tailored to the downstream task. If you contrast this to other closed-loop approaches that also try and incorporate some knowledge of the downstream task, the two main approaches that I've done here is basically assuming that you already have a stable system, and all you're doing is learning a feed-forward correction to the nominal reference signal, or you're trying to learn a correction to a known control Lyapunov function for the system. In this case, we're really starting from absolutely no assumptions at all. We want to learn the full dynamics model and still be able to give some sort of a stabilizability-based guarantee. But we need some sort of an algebraic representation of what stabilizable even means for nonlinear systems. But this is exactly what the first part of the talk essentially established. It established a clear way of defining algebraic conditions that gives you a certificate of stabilizability. So we can rewrite our dynamics problem, and we can replace the stabilizability constraint with just the condition that for a control alpha n model plus some regularization term, there exists a contraction metric m of x for this dynamic system. And then we can go ahead and replace that matrix m of x with its inverse, with w, and this is an equivalent transformation. But the nice thing here is that now our conditions are convex. If I fix the dynamics functions, and if I fix lambda, I have a set of convex constraints. And vice versa, if I fix the W matrix, I have just a set of LMI constraints, and once again, a convex optimization problem. The problem, again, comes back to dealing with the infinite dimensional nature of the constraints. So we'll do essentially the learning-based simplification. The first one is that for the equality constraint, we can solve this exactly, simply by imposing some sparsity assumptions on the metric and as well as the dynamics. And then the second cool part is that we're just going to replace all of our actual functional constraints with sample-based approximations. The reason why this is a completely valid thing to do is that these constraints are only a function over the state, meaning that no matter what state sample, state control, state derivative samples you might have, you're free to sample freely within the state space and go ahead and impose these constraints. So what this essentially gives us is a semi-supervised learning algorithm where the demonstration points that make up our supervised set are actually a strict subset of the points at which we impose the constraint itself. We actually went ahead and derived the optimal solution of this optimization problem using some theory in reproducing kernel Hilbert spaces. And what essentially this gives us is that by doing a random matrix feature approximation of our dynamics, so basically a form that looks like features transpose unknown parameters. So in this case, the features are a priori fixed, and we're just trying to learn the parameters alpha and beta j, as well as a similar decomposition for the metric. We essentially get a biconvex problem where we alternate between fitting these two functions, the dynamics, and finding the certificate of stabilizability. Again, the two key points to remember here is that the first one is that we're free to sample this constraint set independently of the demonstration points. And the second thing is that we also do propose some additional sampling-based heuristics to try and keep the problem tractable at each iteration, since these are basically a whole bunch of LMI constraints that we're solving at each time step. So I'll first show essentially the simulation verification that we did of this algorithm. So in this case, we take a planar quadrotor model, and we're going to pretend that we don't know the dynamics. We generated supervised data sets from as low as 100 points and as many as 1,000 points. We learned 3 different models, with fixed basis functions. So all 3 models have the same modeling capacity. So the first one is pure least squares, where there's no regularization at all. The second one is RR, which is ridge regularization. In this case, this is just standard L2 normalization. And the third one is the CCM method, where in addition to the points in our demonstration set, we independently sampled another 2,500 points where we imposed the constraints in the state space. The evaluation task was basically to use the learned model to solve a trajectory optimization problem that takes the quadrotor from an arbitrary initial location to a stable hover, and then basically build a linear feedback controller around that. So this is what the evaluation task looks like in simulation, where in the top, this is a model learned using just 250 points. At the top, essentially, is the model. The red dotted line is the desired trajectory. The blue is the actual follow trajectory for the CCM model. And at the bottom is the model learned with the L2 normalization. And just both quadrotors start from the exact same initial conditions, but there's a drastic difference in terms of the trajectory that was generated, as well as the quadrotor's ability to actually maintain some sort of a bounded error guarantee around this trajectory. We did this for about 120 different initial conditions. And when we drop the number of demonstration points down to just 100 points, we can see a drastic, essentially, difference in performance. The no regularization technique gives you unstabilizable models for nearly all data set sizes. The L2 model, again, is quite poorly performing in the sense that it, again, gives you a lot of trajectories that are performing quite poorly in terms of stabilizability, whereas the CCM model, given the exact same supervised data set and the exact same function capacity in terms of the feature representation, is able to learn a model that's much better conditioned for control, and is actually able to successfully generate and track those random trajectories from those initial locations.
What are the NR and RR comparison points here again? Can you remind us?
Yeah, so NR is simply a model learned with no regularization, and RR is a model learned with ridge regularization, so L2. And then basically the trend that we observe is that as we increase the number of demonstration points, once we get to about 500 and 1,000 points, the difference between the ridge regularization and CCM basically goes to 0, as you would expect, because you basically have, at this point, enough data points to reconstruct the function, whereas the no regularization technique still gives you very poorly conditioned models. We went ahead and then tried this in hardware as well. So in this case, in the simulation case, everything was noise-free. In the hardware case, this was a rather interesting problem. Essentially, what we did is we partially closed some of the feedback loops on the quad to try and restrict it to the vertical plane. And we just learned the dynamics of the quad in the vertical plane. So this now includes all the weird nonlinear effects, such as ground effect and drag in the vertical plane. The evaluation task was essentially we generated a desired figure 8 trajectory, where for each of the learned models, we solved a trajectory optimization problem that gave us this figure 8, and then again, along with the feedback controller that tried to track this trajectory. In this case, we had about 2 minutes of training trajectories, but we subsampled this to just give us just 150 points of state control and state derivative. Now recall that there are just 100 features for each dimension of the state space model that we're trying to learn. So this is really at an extreme limit, a scarce limit of the amount of data that you need to be able to reconstruct this model. So there are 3 segments to this trajectory. Before I show the video, essentially it starts from point A. It accelerates along this top segment to its full speed at point B.
So another question about the function approximator you're using. How many free parameters do you have, just to get a feeling for really how extreme this is for sparsity of data?
So there are about 100 parameters per dimension for the state space model.
Okay.
So 6 states, so you get 600 parameters for F, and then you get 600 times 2 for control, so 1,200 other parameters for control. So once it gets to point B, it completes a full figure 8 trajectory, and then it decelerates along segment 3 back to point A. So this is the performance for the CCM learned model, and so this is it accelerating into the figure 8. And again, you're going to see some non-perfect tracking here of a figure 8. It's roughly a figure 8 shape. I'll show a final sketch of the thing. It doesn't look like it. It grazes the ground repeatedly, and this was replicable with multiple experiments, where it would graze the ground, but it would never crash. And essentially, this is what the overlay of the trajectory looked like. And basically, it's kind of a figure 8. It's a distorted figure 8, which is to be expected given the fact we just gave it 150 points for learning the model. And we gave it an evaluation task that was 30-second long trajectory with feedback control. And in contrast, here's the model learned using standard L2 regularization. It starts okay as it accelerates into the figure 8 and loses all control. And this was basically, again, this was replicated over multiple trials where we observed the exact same behavior. And essentially what ends up happening is that as it accelerates into the figure 8 part, it loses boundedness guarantees because there is no sort of a regularization, control theoretic regularization happening in this model, and basically is unable to catch up to the actual trajectory and ends up crashing. So the main sort of takeaway from all of this learning dynamics work has been the fact that because we sampled the constraints, we essentially get a form of regularization. We get a form of control theoretic regularization that's tailored to a downstream task. We no longer have any sort of stabilizability guarantee because we're not making sure that the constraints are satisfied everywhere in the state space. But this is okay from a learning perspective because all we're getting is a nice control theoretic regularization that's particularly effective when you're learning from small supervised data sets. The question, however, in this case is that typically the dynamics that we're trying to learn for a robot, we already know the dynamics. We have fairly good physical models for them. So the question is what dynamics that you actually want to learn here. So there's been some work, for instance, in terms of learning imitation vector fields, where again, you're trying to learn nice desired closed loop behavior of an output space. But more interesting, I think, is the area of work where given, for instance, a flow field reconstruction from a numerical simulation, which is, again, extremely high dimensional, can we use this technique to essentially learn a latent space dynamics representation where we're using the control theory constraints to essentially regularize that latent space model? In a similar sort of vein, it'd be nice to see if we can extend this to purely output feedback-based control, where the information the space that we're actually learning in is not the state space of the robot, but it's actually the observation space, for instance, from visual tactile sensors, and apply this to manipulation and local immersion tasks. So again, these are problems that are much, much higher dimensional problems, which I'll talk about how to address the scalability issues with, but I think these are much more exciting problems in which if you can learn a latent space dynamics model that's regularized using control theory constraints, it can potentially lead to much more efficient strategies for trajectory generation and feedback control. So I'd like to take the last few minutes just to talk a little bit about some of the extensions and the limitations of the work that I presented so far. I think it's reasonable to say that robots are great at excelling in sort of structured, isolated environments, such as factory floors, or even the lab environment here. But eventually my goal is to create interactive robots that can operate safely and reliably in unstructured domains. So this includes tasks such as collaborative manipulation, disaster rescue, home assistive robots, contact-based manipulation, haptic feedback-based manipulation, as well as autonomous cars. But there's a long way to go from the research that I presented so far and being able to actually achieve some of these tasks. Specifically, some of the key challenges that lie in this way is how we can actually do real-time feedback control and planning for systems that actually involve contact and hybrid modes. How can we actually deal with high-dimensional output feedback spaces rather than the state space of a robot? How can we actually deal with the uncertainty in perception that comes along with domains such as self-driving cars and manipulation? And finally, within context of human-robot interaction, how can we efficiently perform human intent inference in the loop? And so addressing some of the challenges in some of my work, for instance, one of the main limitations is that I did sort of a worst-case analysis in a lot of the robust planning work. And therefore, a nice way to relax that would be to do some sort of online adaptation and try and give some sort of probabilistic guarantees. The second approach is that limitation is that I assumed full state information to be able to realize the feedback controller. And as I mentioned, the key task and the future advancement here is to be able to do this in an output space only using latent space models. And this third one is a really important thing, is that this problem of semi-infinite optimization is not going to go away. Every time you have a nonlinear system and every time you want to give some sort of a stability guarantee, this will always pop up. And therefore, the field in this sort of domain of optimization has somewhat stalled a little bit. And therefore, there are three key future endeavors that I'd like to pursue. First one is to be able to drop the polynomial assumption that comes with sum of squares optimization to try and drastically improve the function space that we're optimizing over. Of course, you can try and use deep neural networks as well, purely as a verification technique rather than as an end-to-end solution. And finally, there's some interesting work that can be done using ADMM or distributed optimization techniques to try and deal with the complexity of such optimization problems. As I mentioned already, all the work that I've done primarily assumes smooth dynamic systems. And therefore, to be able to extend these nonlinear feedback control guarantees and learning guarantees to systems involving hybrid contact modes is an exciting future endeavor, as well as this final aspect of contraction theory, which essentially relied on exponential stability guarantees. So if your true system is not exponentially stabilizable, then that's not really a great constraint to be adding to your optimization problem during the learning process. So essentially what would be nice to see is if we can come up with a hierarchy of relaxations, essentially going from exponential stability all the way to boundedness, that can just give us more relaxed constraints, but still give us better condition models for control. Broadly, these sort of domains that I've talked about fall under the three main paradigms of learning-assisted control, optimal synthesis, and more recently, as I talked about the DeepMind work on verifiable learning, where I'll just put one final slide on the notion of verifiable learning as one of the key sort of bottlenecks to being able to achieve real-time robust autonomy, where the sort of challenges that we need to be able to address include things like how to understand how uncertainty propagates through deep neural networks, and how we can actually generate provable guarantees and runtime assurances for any learning-enabled component within the loop. And this obviously naturally involves being able to detect regions of poor confidence. And a lot of this future work is inspired by some of the recent work we've been doing with the DARPA Assured Autonomy program, where the idea is to take an airplane and have it do completely autonomous on-ground operations using learning-enabled components in the loop, and being able to give these sort of guarantees, such as being able to give provable guarantees in terms of runtime assurance, as well as being able to detect when you can and you can't detect the output of your deep neural networks. So hopefully I've given you a brief sort of overview of why it's important to be able to reason about uncertainty and robustness at all levels of the autonomy stack to create robust autonomy. And I'd like to just thank all my funding sponsors at this point as well. So the next few slides are interesting, and I'd just like to thank various people. So I would like to begin with all my co-authors. Been very fortunate to work with a lot of talented people at Stanford, outside of Stanford, and within industry as well. And I'd just like to thank everyone, and I know some of them are in the room and some of them are on the cast as well. I'd like to give a particular shout out to these three people, Benoit, Zijan, and Joe, for being extraordinarily patient during all of the hardware experiments. You already saw the blooper reel, but just times that by 2 years, and you can sort of understand that, that these three people have put in a lot of effort to help me through and get these final set of hardware experiments. Next, I'd like to thank my committee, Professor Okamura. Thank you so much for agreeing to be the chair. Professor Rock, I'm going to just go ahead and say this now so that this is a calculated risk that the class. Yeah. We'll get to you. I will still say this, that the class on aircraft stability and control was definitely one of my favorites at Stanford, and will remain my favorite. I still liked optimal control. It's okay. Professor Shager, thank you so much for also agreeing to be part of both committees, and thank you for all the help during the job search process as well. Professor Slotine, if you're still there, thank you so much. You've basically been a co-advisor for all these years, and thank you for always being available for talking about all things control and robotics. And again, I really appreciate your guidance during this job search process as well. Marco.
I don't like this silence.
There are various things I could say. We've had a very wide range of discussions, from everything to do with academia and not with academia. But I'd like to mention two main things. The first one is that I'd like to thank you for always continuously pushing me to not settle for just adequate and not mediocre results. And it didn't matter whether it was a technical paper or a presentation or another funding report. You always pushed me to do the best writing that I could and the best research that I could, and therefore I really appreciate that. And the second one I think is really important, not just for me, but for a lot of new students starting out now, is that you were extraordinarily patient with me as well as I started out. It took a number of failed projects at the beginning to finally settle on my final research path, and you continued to fund me and didn't lose faith, so I really do appreciate your support during all of that. Next, ASL and associated members of Stanford. It's been a pleasure to witness and go through two generations of ASL, starting with the one on the right when we all started out with Marco, as well as ASL 2.0 on the left, the European/Swiss invasion. And just a big thank you also to all the friends I've made in orchestra as well, some of whom are here. And that's just Benoit at hitting his absolute limit at this point and just couldn't take it anymore. And then a big, huge thanks, of course, to my family who've put up with my occasional rudeness, with me being short on videos, not calling enough, not going home enough. And they've really put up with a lot over the last 6 years, and therefore I'm hugely and unbelievably grateful to everything that they've done for me and supported me through the last however many years, far too many years. So yeah, with that, I'll open it up to questions. Thank you so much for coming. Ed.
Great talk. So with regards to stabilizing dynamics, I think that the nice thing about the quadrator is that you know, of course, that your hypothesis is true, that there is a stabilizing control over quadrators.
Yep.
And so therefore, I think like the voting framework makes a lot of sense. When it comes to sort of extending it to different sorts of dynamics, especially like weird flow fields and stuff,
Yep.
Maybe it's not stabilizable, and maybe when you're learning, like your regularization will just project it to some stabilizing controller or something. Like, do you have any thoughts on what happens when your hypothesis maybe isn't the case?
Yeah, so two things essentially happen. The first one is that the algorithm basically stalls when the underlying system is not stabilizable.
Right. Yeah.
Basically, it won't be able to satisfy the constraints, so you get an early termination where the model basically equals the L2 regularized model. In the second case, I think even if the underlying system is not stabilizable, this can essentially be used as a technique to diagnose an unknown dynamical system or a flow field, for instance, where in the sense that you can use this as a design and analysis tool to essentially figure out why the underlying system is not stabilizable and try and figure out what corrections you need to make to the underlying physical system so that you can actually learn a stabilizable representation.
If there's like a submanifold on which you only care about stabilizability, you also just sample only those points and have your constraint.
Right, because you're free to choose the points where you want to satisfy the constraints. If you already pre-select that manifold, then yeah, you can again just do the constraints there. Kunal.
Maybe you want to repeat the question so that.
Oh, Jean-Jacques, did you get the question?
Yeah. So one question, if we go to slide
62.
On the which dynamic?
Which dynamics to learn? Yep.
Yeah. So, Sumeet?
Yeah.
Question from faculty will come in the first session.
Okay, Jean-Jacques, we'll come back to the.
Latent space control dynamics for high-dimensional systems and high-dimensional lattice space dynamics. So in these two applications, the last two out of three.
Yeah.
Apart from dimension, what other difficulties do you expect? How hard do you expect this to be? After all, if you take the third one, high-dimensional space dynamics, it's extremely general, I think.
Right. Yeah.
All that almost anything robotic.
There are two main limitations. The first one is to come up with an appropriate notion of stabilizability for contact-based systems. It's probably going to, again, involve some form of semi-infinite optimization, so that's the first challenge. And then the second challenge is actually being able to formulate the correct lane space representation. So in this case, typically lane spaces are learned using just based on reconstruction error from the lane space propagation of the dynamics. So in this case, it's not clear how you want to essentially learn that lane space representation or even parameterize that such that you can learn something that's useful for control. So it's both from a learning perspective and from a control perspective where the two main challenges are. Kunal, yep.
Yeah, so when you're learning stabilizable dynamics, were there any restrictions on the way that you parameterize the dynamics model? Like if I just gave you some really weird mixture of like a rigid body model with some neural nets in places,
Yeah.
Could you just take that and apply a method to it, or does it have to be parameterized in a specific way?
No, so the linear parameterization was done purely because we had optimality guarantees, because it was from an RKHS perspective. But the constraints can be done in a fully non-linear, non-convex formulation, so deep neural network or any other formulation that you have is perfectly fine as well. Yeah. Yeah.
For the figure 8 experiments, you said you used very little data points. If you used more, would you get close to the actual model? Like,
Yeah, so I didn't show the video, but basically once you have enough data points, then the two models basically give you the same level of performance. And I have some numbers as well that basically show that when you compare the RMS and the max tracking errors, it's basically on par. So essentially, the main sort of advantages really comes from when you're learning from small data sets. And therefore, when you extend it to much higher dimensional models where you do have limited data, this is what ideally we would hope sort of generalizes to that setting.
What would be a good target system for doing that, where it's like really hard to get a lot of data for a high-dimensional system? Is there something that's...
Yeah, I mean, the main sort of systems that we want to obviously target are, for instance, flow field systems are really difficult to get data from because all the simulations take a really long time. But I think a much more exciting domain for me personally would be in the locomotion domain, where it costs a lot of money if your robot crashes and fails. And therefore, keeping able to give some sort of a stabilizability guarantee in terms of the operating limits of your locomotion is super important, obviously. Yeah.
Two questions. The first one, so you mentioned the fact that it would be interesting to learn dynamics for high-dimensional systems. So for me, like I'm guessing for the teacher it would be like PhD systems. So my question is like, it's pretty interesting because right now what you're trying to learn should be like an operator between like subless spaces. So I was wondering, do we have already like contraction theory for this kind of infinite dimensional spaces?
There are contraction theory results for PDE systems. They look horrendously complicated, which is why, again, we don't want to restrict ourselves to only use regularization with contraction theory. And that's sort of one of the future extensions of how you can formulate much more general conditions that are a little bit more relaxed, that potentially might play nicer with if you want to learn PDE systems, or any sort of finite element discretization model for it.
The other question is a little more technical, but proof of the contextual matrix. If you can go to the slide. I don't remember the name exactly, but on the first one. Yeah. Just to correctly understand. So basically, you are trying to select in a cube that is like minimizing your energy. I guess that among these cubes you have geodesics, right? But it really depends on the distance, right, where you are, because geodesics are only locally minimizer, right? Yeah. So what are you doing to deal with, I guess, like conjugate points?
So what we actually, so the reason why a full proof and I have a time derivative here instead is that when you have conjugate points and you have essentially the point might be on the cut loci, you replace the time derivative with the upper right Dini derivative. And so the proof still goes through where instead of an equality that you get in terms of where the time derivative equals the -2 lambda e, you essentially get an upper bound when you use the upper Dini derivative.
So you're not basically limit itself but upper and lower bound?
Yeah, so I mean, that's sort of the nice benefit that even if it's a conjugate point, it doesn't matter because you get an upper bound on the time derivative of the Dini derivative.
So you basically just deal with geodesics here?
Yeah,
okay.
Exactly.
Okay.
Yep.
At what point, circling back to the figure 8 experiment, at what point did you see the data points drop off for the RR performance? Because obviously we saw in the experiment that it just couldn't perform, it would just crash out.
Yeah.
What was like the lower bound for that performance where like you provided enough data points to the RR equation where it like matched?
Where it basically started to?
Yeah, exactly.
Yeah, I think we, both in simulation and in experiments, once it basically hit around 250 to 300 points, it was basically, at least it was boundedly stable. Okay. And once it was at 500 to 1,000 points, it was actually reasonably good. Yeah. Yeah.
Just like building on what I like, the first one is like how did the number of training points compare between your method and the RR? Like, did you get a perfect figure 8 like twice as fast as they did? Basically, like with half the samples, like how many?
Oh, right. Yeah. So that's not a comparison that we did. We basically always fixed the number of samples for both models and compared the learned models side by side. But that's actually interesting to see how many minimum number of samples you need for the two different models to get same level of performance.
Then you can quantify like how much more efficient you are.
Right. Yeah, that's a good point. Joe.
How do you learn the contraction rate?
The contraction rate?
Yeah, that contraction parameter?
Yeah. So when the model is known and you're just searching for a contraction metric, then the optimization problem essentially involves a line search of a contraction rate. And for each contraction rate, you find the optimal metric. So essentially, the performance function that we optimize is the tracking error bound that you get as a combination of the properties of the metric and the contraction rate. When we were doing learning dynamics, lambda essentially becomes a hyperparameter. So in this case, we just set lambda to be something small like 0.1 and just fixed it and ran the learning algorithm just with that. You can incorporate lambda into the optimization problem as well, but that basically just makes the problem more complicated than it needs to be.
Just imagine if you set it, you choose a value, and it turns out you can't actually solve it. You can't find this CCM. Then you'll have to start backing off on that parameter.
Exactly.
And it ends up being sort of this iterative layer on top of your solution.
Yeah. So for the robust planning work, that's definitely. We essentially gridded up lambda, which is just a single variable. And then for each lambda, we've computed the optimal metric. And basically, there was a cutoff where above a certain lambda, the qualities of the metric were so poor in terms of condition number that basically you're approaching the theoretical limit of the stabilizability. Yeah.
I have a tangent, which is I think any company in the world would be very excited to have you, and you would make that company in the world a better place. However, I also think that any academia would sincerely benefit from you as well as all of the students, and I'm curious, as you were my mentor at NASA when we were both interns, I'm wondering if you have plans to return to academia someday, because you have a unique knack for not only knowing the material, but breaking it down into understandable realms that others can understand.
I would say yes, there's a definitive plan to return. That's all I can say until I get an offer, right?
The world will be a better place when that happens.
Could you say that to my prospective employers?
Yes.
Thanks. Yeah.
I had a question. So do you know how much you lose when you make the ellipsoid outer bound over the energy ball?
Yeah, so that's a good question. Actually, I have some results on that. So essentially, we did about 50 hours worth of simulation on the quadrotor. And essentially, what we did is we basically ramped up the disturbance level until essentially a violation of the theoretical bound occurred. And what essentially I'm showing here are the CDFs of the tracking errors, just rotated 90 degrees. And so as you go from left to right, the disturbance threshold is increasing. The horizontal colored lines basically give you the theoretical upper bound. So basically, the colored shaded part should always be below its appropriate colored horizontal line. But what you can actually see is that as you increase the disturbance level just by a little bit, you actually end up violating the bound from the smaller disturbance threshold, almost with just a 0.05 change in the disturbance. This actually tells you that these results are actually not that conservative, both in terms of absolute tracking error, and the similar trends also holds in terms of the outer ellipsoidal approximation as well. Yep, Joe.
Can you bound the control from the differential portion?
Yeah, so for certain classes of metrics, we can give formal guarantees in terms of the control. And if it doesn't fall into that class of guarantees, we essentially augment the control by treating, instead of taking the actual control as your control input, you take its time derivative as your input, and you make the control party a state. You give the guarantee there in terms of the state representation, and then you just deal with the derivative part by filtering it. Myro.
You've done a lot of language research. What is the part of your work that most fun with?
I'm not going to say quadrotors because Benoit knows that's a lie. But I would say difficult to choose. It's sort of bittersweet, actually. Most of the robust planning work and the learning dynamics work, even though it involved a lot of difficult hardware experiments and the pain, it was still probably, I think, what I enjoyed the most. So maybe not so much of a lie. Yeah. I don't know. Difficult to say. Cool. I think, is that it? Great. Thank you, everyone, for being here.